Hi, so today we've got this problem called subarrays with product less than a target. The problem statement is that we are given an array with positive numbers and a positive target number. Find all of its contiguous subarrays whose product is less than a target number. So we've got, for example, 2, 5, 3, 10, and the target is 30. So we need to find all the subarrays. Yeah, so subarrays are basically contiguous smaller arrays in a larger array. So for example, 2, 5 is a subarray, 2, 5, 3 is a subarray, 5, 3 is a subarray, etc. 2, 5 and then 10 is not a subarray because there is a gap in between. It has to be contiguous. So in this example, there are 6 contiguous subarrays whose product is less than a target. 2, 5, 5 and 2, which is 10, 3, 5 and 3, which is 15, and 10. So obviously, if the target is less than 1, then there would be no possible subarrays because these are all positive numbers. And there isn't a positive number less than 1 whose product can return us something less than 1, obviously. Okay, so the solution today that we're going to be using is basically a sliding window with two-pointer. And let me go through the code that I've written for this solution. So the first condition, as I mentioned, is if the target is less than 1, then we obviously return an empty list. And then we're initializing result as an empty list. This is what we're going to return. So it's going to be a list of lists or a vector of vectors. The subarrays are going to be lists inside this result list or arrays. So we start off by initializing left and right as 0. Those are the two ends of our sliding window. Prod is we're gonna be tracking what the product is at any point of time inside that window with prod. It's 1 because it's 0. It's 1, not 0, because the multiplicative identity is 1. Now, the next thing we do is we say, right, so we start a while loop where right is less than length of array. So we really don't care about the left pointer here because, for example, if in an edge case where the left pointer does not even move from here and the right pointer reaches all the way till 10 and maybe even passes 10 and goes above, for example, if the target here was, I don't know, let's say 10,000, then obviously multiplying all these numbers will not still give us 10,000. So that means that right will pass this. In our code, if that happens, we will still get all the sub-arrays required, including 2, 5, 2, 5, 3, all of this, even if right goes beyond the array and left does not even move. So essentially, we're only worried about right reaching till the end of the array. The left will follow. The left will basically close in the window as and when required. We don't need to worry about left, except for one small tiny edge case, which I'll show in the code. So, we've set this condition, we've set this while loop. The next thing we do is we add the element at the index right into prod, and then we check if prod is actually greater than target. This is where we then move left towards the right. Now, there might be a case where left goes beyond the array, and then we would get array out of bounds error. Now, this is important. So when will this happen? So let's say, for example, we have a single array of I don't know, let's say 10, and the target is equal to 2. So right and left is equal to 10. We include 10 in the product, and instantly it's greater than 2. So we cannot use this. So left will try to go towards the right, and obviously even if it removes 10 from product, it's going to go out of bounds of the array. So we have to add a check over here that left is always inside the array while we're increasing left. So yeah, if the product is greater or equal to the target, then we will divide the element at the left index from product and then increase left. Um, Now is the very important part. This is basically the algorithm of this question, and we've also used this with triplets with smaller sum. Um, is how to add those individual elements or subarrays into our result. Now, if this question only asked for the um, the number of subarrays that we can make, so here it's 3, 4, 5, 6, 7, then all we had to do here was right minus left plus 1. Because then, if left is over here and right is over here, then basically, because we need because 826, let's say, is less than 50, the multiplication of 826 is less than 50. If we move our right to 2 over here, 8 and 2 will obviously still be less than 50 because it's less than 826. If 826 was less, 8 and 2 will obviously be less, and 8 will also be less. So that's why it's right minus left plus 1. So 0, 1, 2, 2 is the index, 2 minus 0 plus 1. So 2 minus 0 is 2, and then plus 1 is 3. So you can see that 8, 2, 8 and 2 is what we're getting from these three elements, right? So because we need to find the actual subarrays instead of the number of subarrays, what we're going to do is we're going to traverse the sliding window from the right to the left. So let's say, for example, let's just say let's say our sliding window is at 6 and the left is at 8. And I know 8 times 2 times 6 is greater than 50, but let's just say it's not. Okay, let's just say this is, I don't know, 800. So 826 is obviously less than 800. What we do is we traverse from the right. So the first thing we have is this element, 6. We add that to temp. Now temp has 6 in it, and we make sure that we insert it at the start of the temp array, and this is important if the question asks for the order of the subarrays. So here, as you can see, 8 and 2, it's 8 and then 2, because in the actual array 8 is before 2. Now if the question does not care about the order, then we can add it after, like we can add the 2 after 6, so then it will be 6 and 2 instead of 2 and 6. But here, since the order is important, we want to add any new element in temp before it. So, and because we're traversing from the back, the next element is going to be 2, and we would want to add 2 before 6, so that when we add temp into our result, we will maintain the order of the actual array. Now more on this later, but first we've added 6 to temp, and now this is one of the subarrays of the sliding window, so we want to add this to our result. So that's what we're doing, we're appending what we have in temp right now to result. Now if we just appended temp like this would be pointing, this would be adding a pointer of temp to result. Any further additions to temp that we do, which we are going to do, we're going to be adding 2 and 8 later on, it's just going to modify that pointer. So basically we'll be left with something like 8, 2, 8, and 2, so something like that for these three, instead of 8, 2, and then 8, 2, because all of these three will be pointing to the same temp. We don't want that, so what we're doing is we're sending a copy of temp. What this does is makes a copy of temp and this specifies the start and end, and because we've not specified any start and end, it just copies the entire contents of temp into result. And in the next step, we then move further back to, let's say, 2 over here, add it before 6. Now we have another subarray, and we add that to result as well. So like here, 2 and 6. And this goes on until we've reached the left index. So this is how we get all the subarrays in our sliding window. Now this has been used before as well in triplets with smaller sums. This is an important algorithm to get the number of subarrays or triplets in between the 2 pointers of left and right that we have. Yeah, and if we don't need the actual subarrays, then we can use simply right minus left plus 1 to get the number of subarrays or the number of triplets. Yeah, and the time complexity for this is O of n square, because we have a let me just see if it's O of n square. So we have a sliding window. Yeah, so it is O of n square because for any moment in time we have a left and a right pointer, and then we're traversing from the left and right pointer to add those into result. And the space complexity for this will also be O of n because we're using temp here. That's it for this video, I guess. Yeah, thanks.